What if I told you that the solid, predictable reality you see around you, the chair you're sitting on, the screen you're watching, the very air you breathe, is just the surface? That beneath it all lies a hidden, turbulent, and almost magical world governed by rules so bizarre they defy our everyday intuition. A world of probabilities, not certainties. A world where particles can be in multiple places at once. For decades, this quantum realm has been a fascinating but locked room. We could press our ears to the door, hear strange muffled sounds, but we could never be sure what was happening inside. Until now. Because just recently, a team of scientists at Google didn't just listen at the door. They figured out how to gently knock, and for the first time in history, they heard a clear, verifiable echo from the other side. An echo that not only proves what's in the room, but gives us the key to unlock it. This isn't just another tech headline. This is a turning point in the human story. A moment we might one day look back on with the same reverence we have for the invention of the telescope or the microscope. This is the story of quantum echoes, and it's about to change. Well, everything. Let's start with the headline that rippled through the scientific community. Google announced a monumental achievement, a new quantum algorithm they call quantum echoes. Running on their latest quantum processor, a chip named Willow, it performed a specific, complex calculation an astonishing 13,000 times faster than what is possible on the most powerful supercomputer on Earth frontier. Now, it's easy to get fixated on that number. 13,000 times faster. It sounds incredible, and it is. We imagine a supercomputer chugging away for weeks or months on a problem, while this new quantum machine spits out the answer in a matter of seconds. But if you walk away thinking this is just a story about speed, you're missing the entire revolution. The speed is the sizzle. The real stake is something far more profound. Verifiability. Think back to 2019. Google made waves with their quantum supremacy demonstration. They built a quantum computer that could solve a very specific, very abstract mathematical problem that was effectively impossible for any classical computer. It was like building a Formula 1 car and proving it could go 400 miles per hour. It was a landmark achievement, a proof of concept, but there was a catch. The F1 car could only drive on one specially designed track, and the problem it solved had no real-world application. It was a brilliant but contrived demonstration. More importantly, it was incredibly difficult to check its work. How do you know the answer is right if no other computer can even run the problem to compare it with? This is where quantum echoes changes the game entirely. This isn't a contrived problem. This is a calculation that models a real physical phenomenon. And the results it produces aren't a one-off take-our-word-for-it claim. They are consistent. They are reproducible. You can run the experiment again and get the same answer. Other different quantum systems can run it and confirm the results. And here's the most beautiful part. You can go into a real-world laboratory with real-world molecules and see nature itself give you the exact same answer. This is the shift from a supremacy stunt to scientific utility. It's the difference between an F1 car and the first reliable Ford Model T. One broke a speed record. The other put the world on wheels. This breakthrough isn't just about being fast. It's about being right and being able to prove it. For the first time, we have a quantum computation that is not only powerful, but trustworthy. And in science, trust is the only currency that matters. To truly grasp why this is so significant, we have to zoom out. Way out. We have to look at the fundamental drive that has powered human progress since we first looked up at the stars and asked, what are they? Since we first looked at a plant and asked, how does it grow? It's the quest to understand nature at every single scale. For centuries, our tools were extensions of our senses. Telescopes for the impossibly large, microscopes for the impossibly small. We peeled back layer after layer. We went from seeing the cosmos, to planets, to our own world. We went from seeing tissues, to cells, to the organelles inside them. With each new tool, a new universe opened up. Then we hit a wall of staggering complexity. We reached the level of molecules and atoms, the fundamental building blocks of everything. Here, the simple, classical rules of physics that govern a baseball or a planet just break. Reality gets weird. This is the quantum realm, and our classical tools, including our most powerful supercomputers, were simply not built to navigate it. Imagine trying to paint a photorealistic masterpiece using only a giant paint roller. You can get the broad strokes, the general colors, but the fine details, the subtle shadows, the very essence of the image are forever beyond your reach. That's what our supercomputers have been doing when trying to simulate molecular behavior. They are classical machines, built on a binary language of zeros and ones, trying to describe a quantum world that exists in a state of 0 and 1 at the same time, and everything in between. They can approximate, they can guess, but they can't truly simulate. This is the very reason quantum computers were conceived in the first place, an idea championed by physicists like Richard Feynman. He famously said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." He realized that to understand a quantum system, you need a quantum system. You need a tool that speaks the native language of reality. For decades, these quantum devices have been the subject of scientific study. We studied them like a strange new life form, trying to understand how they worked, how to control them, how to keep them stable. We were studying the tool itself. What Google's announcement signifies is a pivotal transition. The quantum computer is no longer just the object of science. It has now become an instrument of science. It's no longer the patient on the operating table. It's the surgeon's scalpel, ready to perform operations we've only ever dreamed of. So, how does this quantum microscope actually work? The name itself, quantum echoes, is a brilliant analogy. Think about how a bat navigates in the dark, or a submarine maps the ocean floor. They use echolocation. They send out a pulse of sound, a ping, and listen for the echo. The way that sound bounces back, its timing, its distortion, its intensity, paints a detailed picture of the unseen environment. The quantum echoes algorithm does something uncannily similar, but on a cosmic scale of weirdness. Instead of sound, it uses a sequence of quantum operations. Here's a simplified breakdown of the process. 1. The row. Ping. The scientists run a complex sequence of quantum operations forward in time on their Willow chip. Think of this as setting up a perfectly still pond of quantum information. 2. The disturbance. Then they do something incredibly subtle. They reach in and gently nudge just one single qubit. It's the quantum equivalent of dropping a single pebble into that perfectly still pond. 3. The unping. Here's where it gets mind-bending. They then reverse the entire sequence of quantum operations. In a classical world, if you played a movie forwards and then backwards, you'd end up exactly where you started. But in the quantum world, that tiny disturbance, that single pebble drop, prevents things from returning to their original state perfectly. 4. Listening for the echo. The final state of the system is not pristine. It carries the faint, ghostly imprint of that single disturbance. This resulting pattern, this echo, is the prize. This echo pattern is a direct measurement of a phenomenon with a wonderfully sci-fi name, the out-of-time order correlator, or OTOC. Don't let the name intimidate you. What it measures is something deeply fundamental: how information or influence spreads and scrambles through a quantum system. When you nudge that one qubit, how did its neighbors react? And their neighbors? How did that single ripple of information propagate through the interconnected web of quantum particles across space and time? The OTOC is a direct window into the hidden dynamics of quantum reality. It's like having a seismograph that can feel the tremors of a single atom's movement across a whole molecule. It reveals the invisible connections, the secret handshakes, the underlying choreography that governs the dance of particles. It is, quite literally, a way of listening to the universe's internal monologue. If the concept is so elegant, why has it taken so long? Because capturing that faint quantum echo is, to put it mildly, ridiculously hard. The analogy in the source article is perfect. It's like trying to hear a single, delicate whisper during a full-blown rock concert. This rock concert is the ever-present problem of quantum noise and decoherence. A quantum system is the most sensitive, fragile thing in the known universe. The slightest stray vibration, a tiny fluctuation in temperature, a single stray magnetic field, even the act of trying to observe it, can cause it to lose its delicate quantum nature and decohere, collapsing into a boring classical state. The information is instantly scrambled, and the delicate echo is drowned out by a tsunami of noise. This isn't a minor engineering hurdle. It's the central villain in the story of quantum computing. Every quantum experiment is a battle against this all-pervading chaos. Trying to measure an OTOC signal has historically been like trying to photograph a ghost in the middle of a hurricane. The signal is so faint, and the noise is so overwhelming, that it was considered practically impossible to isolate. So, what changed? Two things. First, the incredible precision of the Willow chip, which we'll dive into next. It is an instrument of such exquisite fidelity that the rock concert of noise is turned down to more of a quiet hum. But even that hum is too loud. The second breakthrough was a combination of clever noise mitigation techniques and sheer brute force data collection. The Google team didn't just run the experiment once, or 1,000 times, or 1,000,000. They ran it over and over, gathering more than 1 trillion individual measurements. Let that number sink in for a moment. That is more data than has been collected in the sum of all prior quantum experiments in history combined. By taking this colossal number of snapshots, they could use sophisticated statistical analysis to average out the random noise. The random, chaotic shouting of the rock concert, when averaged, fades into a blur. But the consistent, faint whisper of the quantum echo, because it shows up the same way every time, begins to emerge from the static. They weren't just listening harder, they were listening smarter, and for longer than anyone ever had before. It was an act of both scientific elegance and monumental persistence. At the heart of this entire saga is the hero of the story, the Willow quantum processor. To understand why Willow is so special, you need to understand a frustrating paradox that has plagued quantum computing for 30 years. It's called the scaling problem. In classical computing, more is better. More transistors on a chip make it more powerful. Simple. In quantum computing, it's been the opposite. As you added more qubits to make the computer more powerful, the system became exponentially more complex and fragile. The noise we just talked about would grow, and the error rates would skyrocket. Making a bigger quantum computer often just made it a worse quantum computer. It was a vicious cycle that seemed to put a hard ceiling on progress. Willow smashes through that ceiling. Through a series of engineering and materials science breakthroughs, Google's team built a chip with superconducting quantum gates that operate with a level of accuracy never before seen. The fidelity is so high that the errors accumulate much, much more slowly. Think of it this way. Imagine you're building a tower out of Legos, but each Lego brick is slightly warped. With just a few bricks, your tower is mostly fine. But as you build higher and higher, those tiny individual imperfections compound. The tower starts to lean, wobble, and eventually it collapses under its own accumulated error. That was the old way. Willow is like having a set of almost perfectly molded Lego bricks. You can build a much taller, much more complex tower before the tiny imperfections even begin to matter. This allows scientists to run deeper calculations, long, complex sequences of operations, like the forward and reverse process of quantum echoes, before the whole system decoheres and the calculation is lost to noise. This unprecedented accuracy is what gives scientists that superhuman hearing. It's not just about filtering out the noise after the fact. It's about building a machine so quiet and so precise from the ground up that the whisper of the quantum echo is captured with stunning clarity in the first place. Willow isn't just another incremental improvement. It represents a fundamental shift in the very architecture of what a quantum processor can be. This is the moment where everything we've talked about, the theory, the hardware, the algorithms, leaves the realm of the abstract and makes contact with the real world. A new scientific tool is only as good as the discoveries it enables. So, what was the first thing Google did with their new quantum microscope? They pointed it at molecules. In a landmark collaboration with chemists at UC Berkeley, they used quantum echoes to analyze the structure of two different molecules, one with 15 atoms and a more complex one with 28. Specifically, they were trying to map the relationships between the hydrogen atoms within these molecules. The traditional, gold standard method for doing this is a technique called nuclear magnetic resonance, or NMR. It's the technology behind MRI machines in hospitals, and it's been a cornerstone of chemistry for decades. It's powerful, but it has limits. Think of NMR as giving you a slightly blurry, black and white photograph of the molecule. You can see the big features, but some of the finer details and long-range connections are lost. The team first used quantum echoes to predict the NMR signals for these molecules. They ran the quantum simulation on the Willow chip, and out came a prediction. Then, the UC Berkeley team went into their lab and ran the actual real-world NMR experiment on the physical molecules. The result? A perfect match. The quantum computer's prediction perfectly mirrored the measurement from physical reality. This was the first critical step, proving that the simulation was accurately reflecting the real world. But then, they did something even more extraordinary. They pushed quantum echoes to look beyond the limits of classical NMR. Because of its incredible sensitivity, the quantum simulation could detect the faint, long-range correlations between atoms that were far apart in the molecule, details that are completely invisible to standard NMR experiments. It was like the black and white photograph suddenly blooming into full-color, high-definition 3D. They weren't just replicating an old experiment. They were discovering new information about molecular structure that was previously inaccessible. This was the first concrete, verifiable example of a quantum computer extending the boundaries of human scientific knowledge. Okay, so we can map atoms in a molecule with a bit more precision. Why is that a world-changing event? Because understanding the precise three-dimensional structure of a molecule, its exact shape, and how its atoms are connected, is fundamental to nearly every modern industry. It's the master blueprint for innovation. Let's take medicine and drug design. Most diseases are caused by malfunctioning proteins in our bodies. Drugs work by binding to these proteins, like a key fitting into a lock, to either block their function or change it. The problem is, it's incredibly difficult to know the exact shape of the loci. Loci, the protein, and to design the perfect new key, the drug molecule. For decades, this has been a process of brute force trial and error, costing billions of dollars and often taking more than a decade to bring a single new drug to market. Now, imagine if you could use a tool like quantum echoes to perfectly simulate the interaction between a potential drug molecule and a target protein before you even synthesize it in a lab. You could test millions of variations in a computer, find the one with the perfect shape and binding properties, and move forward with only the most promising candidates. This would transform drug discovery from a game of chance into an act of precision engineering. It would slash R&D costs and accelerate the development of life-saving medicines for everything from cancer to Alzheimer's. And it doesn't stop there. This same principle applies everywhere. Energy. Want to build a better battery? You need to understand precisely how lithium ions move through the molecular structure of an electrolyte. A quantum simulation could help design new materials for batteries that charge faster, last longer, and are safer. Climate change. To create more efficient solar panels, you need to model exactly how a photon of light interacts with the crystalline structure of silicon to release an electron. To develop better catalysts for carbon capture, you need to simulate how CO2 molecules bind to a material surface. Materials science. From creating self-healing plastics to designing room-temperature superconductors that could revolutionize the power grid, it all comes down to arranging atoms in just the right way. Understanding molecular structure isn't just a niche scientific pursuit, it is the foundational challenge that unlocks progress in medicine, energy, technology, and beyond. Quantum Echoes provides a universal key to that challenge. Let's circle back to that crucial distinction between the 2019 supremacy experiment and today's utility breakthrough. It's a point worth hammering home because it represents a maturation of the entire field of quantum computing. The supremacy demonstration was like a brilliant but esoteric piece of performance art. It was designed to prove a point, that quantum mechanics could offer a fundamentally different and more powerful mode of computation. It succeeded, but the task it performed was solving a random circuit sampling problem. It's a task with no known practical value, chosen specifically because it's incredibly hard for classical computers. It was a benchmark, not a tool. Quantum Echoes is the opposite. It tackles a problem that scientists have been wrestling with for decades: simulating quantum systems. It provides an answer to a question that chemists and physicists actually care about. The goal wasn't just to be faster than a supercomputer for the sake of it. The goal was to produce a scientifically valuable result. This is the difference between proving you can lift 1,000 pounds and actually using that strength to build a house. One is a demonstration of power. The other is the application of that power to create something useful. Furthermore, the 2019 result was a black box. The quantum computer gave an answer, and while there were clever statistical ways to argue it was probably right, it was fundamentally unverifiable. This new work is built on a bedrock of verification. The results are repeatable on the quantum machine itself. They are confirmable by other quantum machines. And most importantly, they are validated by experiments in the real world. This closes the loop. It creates a chain of trust from the quantum simulation to physical reality. It's the moment the field graduates from making bold claims to producing cold, hard, verifiable facts. For years, the biggest question haunting the quantum computing field has been a deeply philosophical one. How do you know the answer is right? When you're dealing with a machine that operates on principles that defy common sense, and it's solving problems that no other machine can check, how can you ever truly trust its output? It's a crisis of faith that has held the field back. Quantum Echoes offers the first robust answer to this question, and in doing so, it kicks off what we might call the verification revolution. The solution is a three-pronged approach to establishing scientific trust. 1. Cross-platform verification. The principles behind quantum echoes are universal. This means that another research group with a completely different type of quantum computer, say one based on trapped ions instead of superconducting circuits, could run the same experiment. If they get the same result, it dramatically increases confidence that the result is a feature of the physics being simulated, not a quirk of Google's specific hardware. 2. Experimental verification. As we saw with the UC Berkeley collaboration, the results from the quantum computer can be directly compared to real-world lab experiments like NMR. When the simulation and reality agree, it's the most powerful validation possible. It grounds the abstract computation in tangible physical fact. 3. Theoretical verification. For simpler systems, scientists can still calculate theoretical predictions. If the quantum computer's results match these predictions on the simple cases, it builds trust that its results on the more complex, unsolvable cases are also correct. This multi-layered system of checks and balances is how all good science works. And now, it has finally come to the quantum realm. This creates a path to a future where quantum computers don't just work in isolation. They can form a self-consistent network. One machine could run a simulation, and another could be used to verify its results. They could validate each other, building a web of interconnected, trustworthy quantum knowledge. This is the foundation upon which the entire future of the field will be built. Without trust, a quantum computer is just a novelty. With it, it's a tool for discovery. Google likens this moment to the invention of the telescope or the microscope, and I believe that analogy is not an exaggeration. It's perfect. Think about what the telescope did for humanity. Before Galileo, we looked at the sky and saw faint, wandering lights. We had myths and theories, but we couldn't truly see. Then, Galileo pointed his telescope at Jupiter and saw 4 tiny moons orbiting it. In that instant, the universe changed. It wasn't just a new data point. It was a fundamental shift in perception. It proved that everything did not revolve around the Earth. It opened up the cosmos and gave birth to modern astronomy. The microscope did the same for the inner world. Before Van Leeuwenhoek, we believed in vague concepts like miasma to explain disease. Then he looked through his lens and saw a teeming world of animalcules in a drop of water. The germ theory of disease was born, and modern medicine became possible. These tools didn't just help us measure things we already knew about more accurately. They revealed entire layers of reality we never knew existed. They expanded the very definition of what was perceptible to humanity. Quantum echoes is a tool of that same caliber. It is our quantum microscope. For the first time, it allows us to observe directly the subtle, high-speed dance of information within molecules, materials, and perhaps one day, even the quantum foam of space-time itself. It's not just a better calculator for chemists, it's a new set of eyes for physicists. It is a tool that will allow us to ask questions we previously didn't and even know how to formulate, unlocking the next great revolutions in our understanding of the universe, from the smallest particles to the largest structures. So, where do we go from here? Google has been very open about its roadmap, and the next grand challenge is what they call Milestone 3, creating a logical qubit. Everything we've discussed so far has been accomplished using noisy physical qubits. They are brilliant but flawed, like a genius musician who occasionally hits a wrong note. They lose their quantum state very quickly, which limits the length and complexity of calculations. A logical qubit is the holy grail. It's an ingenious concept where you use many physical qubits working together, constantly checking each other and correcting errors in real time. This collective would act as a single, ultra-stable, virtually perfect qubit that could maintain its quantum state for hours or even days. Achieving a long-lived logical qubit would be the gateway to fully fault-tolerant quantum computers, machines that could run unimaginably complex algorithms without being corrupted by noise. That is still the ultimate goal. But what quantum echoes so powerfully demonstrates is that we don't have to wait for that perfect, error-corrected future to do meaningful science. The current era of noisy intermediate-scale quantum, NISQ devices, powered by chips like Willow, are already proving to be incredibly useful. This discovery acts as a vital bridge. It proves that even with today's imperfect technology, we can extract real, verifiable, and valuable scientific insights that are beyond the reach of classical machines. It provides immediate utility today, while paving the road toward the flawless quantum computers of tomorrow. Google has put a bold timeline on their ambitions. They predict real-world, commercially relevant quantum applications within the next 5 years. This might sound audacious, but consider the evidence. With quantum echoes and the Willow chip, they've already demonstrated verifiable quantum advantage on a real scientific problem. The remaining challenges are now largely about engineering, scaling, and refinement, not about discovering brand new, unknown physics. The foundational proof is here. If this exponential pace of progress continues, we are standing on the cusp of a new computational era. Within the next decade, we could realistically see the first drugs designed with quantum precision, breakthroughs in battery technology that transform our energy grid, and the creation of novel materials that exist today only in theory. But as we stand here, looking at this incredible technological horizon, I think there's a deeper, more human lesson to be drawn from this story. It's a lesson about listening. The universe is a noisy place, and our lives are too. We are constantly bombarded by information, by distractions, by the rock concert of everyday existence. The biggest breakthroughs, the most profound insights, whether in science, in business, or in our own personal lives, rarely come from the loudest voices. They often start as a faint whisper, a subtle signal, a tiny echo that is all too easy to dismiss as noise. The genius of the team behind Quantum Echoes was not just in building a quieter room, but in developing the patience and the technique to listen for that whisper. They showed that with the right tools, immense persistence, and a willingness to believe in the significance of a signal that others couldn't hear, you can uncover a hidden reality. So, my advice, drawn from this incredible story, is this. Learn to listen for the echoes in your own life. Pay attention to the quiet signals, the subtle patterns that others overlook. Cultivate the focus to filter out the noise, because somewhere in that quiet space, you might just find your own breakthrough, your own new way of seeing the world. The journey from a theoretical idea to a world-changing tool is a long one, but today we've taken a giant leap. We've learned to hear the universe's quantum whisper, and now I want to turn it over to you. As you think about this incredible new capability, what potential application excites you the most? Is it a cure for a disease, limitless clean energy, or something else we haven't even imagined yet? Let me know your thoughts down in the comments below. I read every single one. Thank you for joining me on this incredible journey into the quantum realm. I hope it's left you with a sense of wonder and optimism for the future we are building together. And if you enjoyed this deep dive and want to stay ahead of the curve on the breakthroughs that are shaping our world, do me a favor and hit that subscribe button and ring the notification bell. It truly helps the channel continue to bring you stories like this.